11.4 Limits. First question, what is meant by limit of a function? The limit of f of x as x approaches a equals L, written as the limit of f of x as x approaches a is equal to L. Right? That the part that's highlighted is the verbalization of what is above. This is true if we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to a. So if you look at the diagram, right, you've got the graph of y is equal to f of x. And we are looking at what happens very close to A. So as you approach A from the left, you can see that the output, right, f of x approaches L, right? And if we approach A from the right, then you can see again that the output for f of x also approaches L. So this is an illustration of what's happening. We now look at examples. Right, example 1, let g of x equal to the split function x plus 2 if x is not equal to 1, and g of x is equal to 0 if x is equal to 1. You can see below that there's an illustration, a graphical illustration for the function g. What is required of us is to evaluate the limit of g of x as x approaches 1. So as x approaches 1 from the left, you can see that the output, right, from the graph, it's approaching 3. As x approaches 1 from the right, right, the output also approaches 3. So therefore, the limit of g of x as x approaches 1 is equal to 3. Now let's look at the second example. Example 2. Let f of x equal to negative 1 if x is less than 0. So you can see that on the diagram below. And you got let f of x equal to 1 if x is 0 or greater than 0. Right? The 0 is there. So you can see the graphical representation. Now, let's see what happens over here. As we approach 0 from the left, right, your f of x, the output, approaches negative 1. So as x approaches 0 from the left, right, this is how we read this out. X approaches 0 from the left. This is how we read this out. Right, so as x approaches 0 from the left, f of x approaches negative 1. Right, and let's check what happens as we approach 0 from the right. So from the right, we're approaching 0. You can see that your output in this case approaches 1. Right, so we can write this as the limit of f of x as x approaches 1 from the right. Sorry, as x approaches 0 from the right is equal to 1. Right, the one above, right, as x approaches 0 from the left, f of x approaches negative 1. We can write this as the limit of f of x as x approaches 0 from the left is equal to negative 1. Now, if we take both of these together, you can see that the limit of f of x as x approaches 0 does not exist, because you're getting two different values as you approach from the left of 0 and the right of 0. Two different outputs. Right, so the limit of f of x as x approaches 0 does not exist. Right, so that's an important problem. So we now go on the next page, theorem 1. Properties of limits. Suppose the limit of f of x as x approaches a is equal to L, and the limit of g of x as x approaches a is equal to m. Then the limit as x approaches a of some function f of x raised to r is the same as the limit as x approaches a of that function f of x, but all raised to r. So you can take the limit inside before you raise the function to r. So this is equal to now L raised to r, where r is a real number. If you look at the structure for number 2, you're dealing with the limit as x approaches a of some constant c multiplied by a function f of x. This is the same as taking the constant out of the limit, so it becomes the constant c multiplied by the limit of f of x as x approaches a, which will now give you c multiplied by L, that's from above. In this case, c a real number. 3, the limit as x approaches a of the sum or the difference of two functions f of x and g of x respectively is equal to the limit as x approaches a of the first function f of x plus or minus the limit of the second function g of x as x approaches a, which is equal to the sum or the difference of L and M respectively. That's from above. Right, so number 3, we're taking really the limit of the sum of the difference of two functions as x approaches a. It is the same as taking the sum of the or the difference of those, the limits of those individual functions as x approaches a. Number 4, right, from the structure, the limit as x approaches a of the product of two functions. This is the same as the product of the limits of those functions as x approaches a. Right? That is what the 4th property of limits indicates. The 5th one, the limit of a quotient, right? A function of a quotient where you've got a numerator and a denominator. You're taking the limit as x approaches a. It's the same as taking the limit of the function in the numerator as x approaches a and dividing by the limit of the function in the denominator as x approaches a. And from above, you do the substitutions for those limits. This is provided that m is not equal to 0. Right? If m is equal to 0, then we'll need some other method to evaluate the limit. So example 3, evaluate the following limits. Now, if you take the first one, 3.1, the limit as x approaches 1 of the function. Here you've got the limit of the difference of two functions. So this is equal to the limit as x approaches 1, right, of the function 2x cubed minus the limit of 4 as x approaches 1. So this gives us now 2 multiplied by, if you take the limit of x cubed as x approaches 1, it's really 1 cubed, minus the limit of 4 as x approaches 1. Your 4 is independent of 1, so it's going to remain as 4. So this gives me now negative 2. Right, if we look at 3.2, the limit of x squared plus 1 all divided by x minus 1, and we're taking the limit as x approaches 2. You can see from that the denominator is not equal to 0 as x approaches 2. The denominator approaches 1. So for this we can use the fourth property above. So it's the same as the limit as x approaches 2 of the numerator. The limit of the numerator as x approaches 2 over the limit as x approaches 2, and we're taking the limit of the denominator. So this gives us now, for the numerator, it's going to be 4 plus 1, taking the limits, all over 2 minus 1, and this gives us an answer of 5. 3.3. The limit as x approaches 1 of x squared minus 1 all divided by x minus 1. As x approaches 1, you can see that the denominator approaches 0. So here we can't use the fifth property, the limit of a quotient, right, of functions. What we can do over here is factorize the numerator. So this gives us now the limit as x approaches 1 of factorizing the numerator, that's x plus 1 multiplied by x minus 1, right, the difference of using the difference of two squares, all over x minus 1. So the factor x minus 1 in the numerator divided by the factor x minus 1 in the denominator, right, that will give us the same factor we're dividing, right, so it's going to give us 1, and we end up now with the limit as x approaches 1, and it's the limit of x plus 1. So this gives us an answer of 2. Right? We now look at a slightly more difficult problem. right? 3.4, you can try that out on your own. I will deal with 3.5. 3.5, you see if you take the limit as x approaches -3, the denominator is going to approach 0, right? You got the quotient of two functions, and the denominator is going to approach 0 as x approaches -3, so we have a problem over here. If you look at the numerator, it's the sum of two cubes. So from school, you know sum of two cubes, right? Say a cubed plus b cubed. Factorize that in the first bracket, right? You take the cube root of the first term, you end up with a, plus the second term, you'll get taking the cube root of b cubed, second term, you'll end up with b, right? You now generate the second factor. It's from the first factor. You square the first term there. That's a squared. Take the product of those two terms. It gives you ab, and you change the sign, so it becomes negative ab, right? Plus the square of the second term in the first bracket. That's going to give us b squared. So if you had, say, the difference of two cubes, in other words, a cubed minus b cubed, then that will equal to a minus b into a squared plus ab plus b squared, right? Factorization of the sum or the difference of two cubes. That's your work from school. So let's continue now with number 5. So the solution for the numerator is going to be a plus 3 into a squared minus 3x plus 9, all divided by x plus 3. So the factor x plus 3 in the numerator divided by the factor x plus 3 in the denominator. So this gives us, simplifies to x squared minus 3x plus 9, right? What I did is I really simplified the quotient of those two functions on which the limit is operating. Now I can take the limit. So now the limit as x approaches -3, right, of x squared minus 3x plus 9, right? All of this goes in brackets because the limit is operating on each of those three terms. So this now is equal to, right, I'll get -3 all squared, which gives me 9, minus 3 multiplied by -3, that's going to give me plus 9, and the limit of the constant 9 as x approaches -3 that's going to give me plus 9. So the final answer here is 27. Right. So we now move on to the next part. So evaluate the limit as x approaches infinity of 1 over x squared. Right, so if you look at this, as x approaches infinity, that for the structure 1 over x squared, your x squared is going to approach positive infinity. So this is very large, right? So your x squared is going to approach a positive infinity. So if you look at the structure 1 over x squared, your 1 is a constant, and you're dividing 1 by very, very large positive values, right? And as the denominator becomes larger and larger, the fraction 1 over x squared is going to approach 0. It's going to get smaller and smaller on the positive side, and it's going to approach 0. Therefore, the limit as x approaches infinity, right? The limit of 1 over x squared as x approaches infinity, this will equal to 0. Make sure you understand that. Now let's look at the next one. We want to evaluate the limit as x approaches negative infinity, and we're taking the limit of the function 1 over x squared. So again, using similar reasoning, as x approaches negative infinity, right? Your x squared, right? You are squaring negative values, so you're going to end up with a positive result, but x is approaching negative infinity, so x squared is going to approach positive infinity, right? And again, this is very large. So 1 divided by a very large number, and the denominator is going to become larger and larger, positive, larger and larger value. So because the numerator is fixed at 1, this fraction is going to approach 0. So therefore, the limit as x approaches negative infinity of the structure 1 over x squared, right, that will approach, will equal to 0. And these two results give us the statement of the next theorem. Theorem 2, right, this is generalizing what's happening above. For all n greater than 0, the limit as x approaches infinity of the structure 1 over x to the n is equal to 0. All right, what we did is we took the case where n is equal to 2 and illustrated it above on the left-hand side. And the limit as x approaches negative infinity of the structure 1 over x to the n is equal to 0, right? Provided that 1 over x to the n is defined. Okay, you should know the result of theorem 2, the statement and the whole statement of theorem 2, and you must be able to apply it. The next question, how do we evaluate the limit at infinity of a rational function? Now recall, a rational function has a structure, a polynomial divided by another polynomial, provided the polynomial in the denominator is not equal to 0. So here, to proceed with a problem of this type, we divide the numerator and denominator by the highest power of the variable present in the denominator. Right, so let's go through this again. Divide. The question is, how do we evaluate the limit at infinity of a rational function? A rational function has a numerator and a denominator, both being polynomial functions. So we divide the numerator and denominator by the highest power of the variable present in the denominator. Right? So let's take an example. Right, we've got example 4. The limit as x approaches infinity of a rational function. Okay, you can see that's the structure of the function on which the limit is operating. So we need to find the highest power of the variable present in the denominator. The variable in this case is x, and the highest power of the variable present in the denominator, you can see it's x squared. right? So you divide the numerator and the denominator by the highest power of the variable present in the denominator. So in this case, we divide the numerator by x squared. So I'm going to do that in the side of here so you can see what's going on. So that's 3x squared plus 5x plus 1. I need to divide that by x squared, right? And then I need to divide the denominator, which is 2 minus 4x squared. I need to divide that by x squared. So I'm dividing both the numerator and the denominator by the highest power of the variable present in the denominator. And that is x squared in this case. So now I simplify. Right? I divide each term by x squared. For the numerator, that's going to give me 3 plus 5 over x plus 1 over x squared. Right? Working out the denominator, that's 2 over x squared minus 4. So, if I go back to the problem, the limit as x approaches infinity of that rational function is equal to the limit as x approaches infinity, and now I can replace it by what's on the right hand side. So that's 3 plus 5 over x plus 1 over x squared, all divided by 2 over x squared minus 4. Now I take the limit as x approaches infinity of each term in the numerator. Right? So the 3 is independent of x, so that will remain as 3. But the limit of 5 over x as x approaches infinity, that's going to approach 0. Right? Plus the limit of 1 over x squared as x approaches positive infinity, this will also approach 0. Right? And if I go to taking the limit of the terms in the denominator, the limit as x approaches positive infinity. So the limit of 2 over x squared, remember now the numerator here, 2, is a constant. So it's some constant divided by a positive denominator, which is approaching very, very large values. This is going to approach, that whole fraction is going to approach 0. So you can see here that taking the limits, I'm going to end up with, for the numerator, it's going to be 3 plus 0 plus 0 all over. For the denominator, I'm going to get 0 minus 4. And this gives me an answer of negative 3/4. Okay. Example 5. I'm going to leave this for you to try out on your own. You'll get the solution in the PDF of the lecture. So you must study examples 1 to 11. That's from page 325 onwards.